Hello, everyone. So last time we were still doing derivatives and differentiation, and we looked at chain rule and some examples, applications, and I also gave you some general examples for derivatives and some exercises that you can work on them. And today we'd like to do a new topic called implicit differentiation. So far, we were dealing with, when I say so far, I mean in this course so far, and also in pre-calculus or high school, when you learned about the concept of functions. So you were dealing with the functions written in an explicit form. So far we looked at functions written in the explicit form. Let's say y equals f of x. So here x was independent variable or input, and y was dependent variable. Okay, so the concept of functions, we also gave a review in the first lecture that, you have for each input denoted by x, you have exactly one output denoted by y or f of x. So this form of the function is called explicit form, because y as a function of x is expressed explicitly in terms of x. For example, y equals x squared, or y equals, let's say, sine x, or let's say y equals, I don't know, log x plus 2x cubed. Right? So left-hand side, you have y, and as a function of x, and right-hand side, you have a formula expressed in terms of x. Okay, so however, well, this is of course a very straightforward form of a function, but sometimes this is not possible. It's not possible to write function in this straightforward form called explicit form. Sometimes it's not possible, or sometimes not easy to do that. So sometimes it's impossible to write y in this form. Sometimes it's not easy to write y in this form. And we have to give a connection between x and y implicitly. So here, basically, the point is there a connection between x and y is given. So when you say y equals x squared, so basically we are talking about a connection between x and y. We are saying that once we have x, we can raise it to power 2 to get y. Or when you say y equals sine x, we are saying that once we have x, we can apply sine function to it to get y. Right? So we can still talk about a connection between x and y, but not of this form, not in the form y equals a function of x, but we can still state a connection between x and y. So however, in certain situations, the connection between x and y is given implicitly, since an explicit connection or explicit relation is impossible or difficult to state. It's impossible or difficult to state an explicit relation. So in those cases, we have to suffice to implicit relation. So for example, equation of a circle. Of the unit circle, let's say. So this is basically x squared plus y squared equals 1. Right? So see, a connection between x and y is given here. But it's not of the form y equals something, right? So this is called an implicit equation. And, you know, for example, in this case, the graph looks like this. So these are the set of all points such that x squared plus y squared is equal to 1 for those points. Okay, so, and by the way, this one is not a function, right? Because, you know, it fails the vertical line test. So note the graph above is not a function since it fails the vertical line test. So you may say, okay, it's not a function, so we shouldn't be concerned about it. It's not a function because there is a vertical line that passes through the graph twice. So you may think that, you know, we shouldn't be concerned about it. Well, yes, it's not a function, but still is a curve, right? So remember, in this course, one of our main goal is to find, you know, the equation of the tangent line. So as long as you have a curve, you can define a tangent line, right? So it's not a function, but still we can define tangent lines, or we can try to find the equation of tangent lines at certain points of the circle. Right? So that's why, yes, it's not a function, but we might be still interested in this graph, or we might be interested in finding the equation of the tangent line. So we still want to have a calculus. We still want to know how we can find, possibly differentiate it or find the equation of the tangent line, even if the curve is not a function. So, however, we still have a curve. In the plane, in the XY plane. And we can still talk about the equation of tangent line. Equation of tangent lines. Tangent lines to this curve. Okay, so let's look at another example. Let's say, for example, x cubed. So consider, before giving the example, so implicit equation, when we say implicit equation, we mean this implicit equation, an equation that gives or provides a connection between x and y. And not of the form y equals f of x. Because if it's of the form y equals f of x, yes, it still is a connection between x and y, but we said that we call that this type of equation y equals f of x, we call it an explicit equation. So explicit equation, on the other hand, means any equation of the form y cos f of x. Okay, so let's look at an example. Let's say y equals ln x. Write this equation in an implicit form. So y equals ln x gives a connection between x and y. But is this connection written in an implicit form or written in an explicit form? Well, we said that if it's y equals a function of x, if left-hand side is y and right-hand side is a function of x, then we call it explicit form. Otherwise, it's implicit form. Well, we just look at here, and the left-hand side is we have y. Right-hand side, we have function of x. So y equals a function of x means it's an explicit form. Right now, it's an explicit form, but we want to write it in an implicit form. Implicit form means, we don't want y equals a function of x, just a connection between x and y equals 0 or equals some constant. To do that, we can just use the definition of log. So to do this, use the definition of log. So what do we have? We have ln x, which is log x in base e equals y. So definition of what a log says what log? So we know that log a in base b equals c. This is the same as saying that a is equal to b to power c, right? So here, e raised to power y is equal to x. My a here is x, my b is e, and my c is y. So we can write this in the form e to power y equals x. So this is an implicit equation for y equals ln x. See, y equals ln x was the explicit form. Now we wrote it in the form e to power y equals x. So still e to power y equals x provides a connection between x and y, but it's not of the form y equals a function of x. Another implicit form, you could write it also, if you take everything to one side, you could say e to power y minus x equals 0. This is also implicit equation for y equals ln x. Okay, so let's look at another example. Let's say x cubed. Consider the equation x cubed plus y cubed equals 3xy. X cubed plus y cubed equals 3xy. So this equation is an implicit equation, since it is not written in the form y equals f of x. See, left-hand side, you don't have just a y, you have x cubed plus y cubed, right? x cubed plus y cubed, and the right hand side is again not just a function of x, you have 3xy. So there's a mixture of x and y, which means that this equation is an implicit equation. X and y are mixed, and just the connection between them is given. So this is an implicit equation. Now, can we write this in the form of an explicit form, explicit equation? Now, can we write this equation in an explicit form? Well, if you want to write it in an explicit form, we have to solve for y. To do that, we need to solve for y. So, because explicit form means what? Means y equals a function of x. So we need to find y here in terms of x. We need to solve for y in terms of x. So what is the equation right now? It's x cubed plus y cubed equals 3xy. So if I take everything to one side, y cubed minus 3xy plus x cubed equals 0. Now this equation is a cubic equation, right? So we do have a formula for cubic equation written in this form, but I think you didn't see it in pre-calculus or high school, right? So I will not expect you to know the cubic formula, but there is a formula for solving, this equation for power 3 if you have a cubic equation. So need to use cubic formula to solve for y in terms of x. So you are not expected to know the cubic formula. Okay, so you're not expecting, but there is a formula. So that's all you need to know, that there is a formula here. But what about, and the graph of, by the way, so we can use a software to sketch the graph for this equation. So it can be seen that the graph will look like this. So this point here is 3/2 and 3/2. Okay, so we just need to use a software to graph because we don't have any idea how to sketch it, but there are softwares that you can give the equation and they will tell you or sketch the graph for you. Okay, so now another example, let's say if you have x to power, let's say y to power 5 plus, let's say 6y to power 4x minus y cube minus 2 sine x equals 7. This is minus 2 sine x plus y equals 7. So this one is an explicit form, or is it explicit equation, or is it an implicit equation? So this is an implicit equation, because again, not of the form y cos f of x. Now, can we write this in an explicit form? Can it be written? In an explicit form. So in other words, i.e., can we solve for y in terms of x? So for previous example, we saw we could solve for y in terms of x, but we need cubic equation, which we don't know about it in this level, but it can be solved using cubic equation. But this one, to solve y in terms of x, we need a formula for solving an equation of degree 5. And there is no formula for solving equation of degree 5. So the answer is no, since there is no formula for solving an equation with degree 5. Okay, so it's not about the two things. Can we solve it in this level, or can it be solved? I always tell the students that there is no solution is not same as I don't know how to solve it. So you have to always distinguish between these two. Are you saying that it cannot be solved, or you're saying that you cannot solve it? Previous example, we said it can be solved, but we don't know how to solve it in this level, like first year calculus course. But this question, I'm saying that not that we don't know how to solve it in this level, it cannot be solved. There is no formula for solving an equation of degree 5 in any level. So no matter what level you're looking at, it can be proved, because you may say, okay, maybe mathematicians have not discovered yet about the formula of degree 5. Maybe in the future they will derive a formula for solving degree 5 equation. But the answer is no, that's not the case. The mathematicians have proved that an equation of degree 5 cannot be solved using a closed formula. There is no formula. There can be no formula for solving an equation of degree 5. So not only they haven't discovered yet, they also proved that it's not possible that in the future someone comes up with a formula for an equation of degree 5. It's not possible. No one can derive a formula for solving an equation of degree 5. Okay, and since there's no formula for solving an equation with degree 5, so we cannot write it in an explicit form. And again, if you want to graph this equation, you can just use a software. Of course, it's very hard to, we cannot solve for y, and we cannot sketch the graph either. If you want to sketch the graph, just use a software to see how the graph looks like in XY plane. Okay, now that we learned about the concept of implicit equation, now we want to learn about implicit differentiation. So implicit differentiation is a given an implicit equation of the form f of, let's say, x and y equals 0, right? See, explicit equation means something of the form y equals f of x. Implicit equation means a function of the form f of x and y equals 0. So for example, 2x squared plus 3y cubed equals 6, or minus 6 equals 0, right? So instead of y equals a function of x, we have a function of x and y equals 0. Like for example, like I said, the function of x and y could be 2x squared plus 3y cubed minus 6 equals 0. So even if originally the right-hand side is not 0, as if your equation was 2x squared plus 3y cubed equals 6, of course you can take 6 to the other side and write it in the form of f of x and y equals 0. So any implicit equation can be written in this form because you have a function of x and y equals 0. In the previous examples, for example, this one, see, this is a function of x and y equals 7, but if I take 7 to the other side, I will have a function of x and y equals 0. Or this one, again, it's a function of x and y in the left-hand side, also equals function of x and y in the right-hand side. But of course, I can take this term to the other side, and then I will have a function of x and y equals 0. So any implicit equation can be written in this form. So given an implicit equation of the form f of x and y equals 0, our goal is to find y prime equals dy to dx. So still, which will give us the slope of tangent line at any given point of the curve. Okay, so still, even if you have implicit equation, we still have a curve. It could be the curve of a function or just a curve that fails the vertical line test, therefore it's not a function. In any case, we'll have a curve, and when we have a curve, we can have tangent lines. How can we find the slope of tangent line? Still same as before, still we need to find the derivative denoted by y prime or dy to dx, and then plug our point to the formula for derivative, and then we'll find the slope. So still we are interested in finding a y prime or dy to dx. In other words, derivative respect to x, in order to find the slope of tangent line at any given point of the curve. Now, how can we find the slope of tangent line or dy to dx in this case? The recipe is that, we have an equation, right? It has left-hand side and right-hand side. So we can differentiate both sides. We differentiate left-hand side, we differentiate right-hand side using the derivative rules. We already know about the derivative rules. So differentiate left-hand side, differentiate right-hand side using the derivative rules. The only thing that you have to remember is that when you differentiate the terms containing y, because y is a function of x, right? So for example, what is y? Let's say if you have y squared, for example. If I have x squared, or derivative of x squared, I know 2x by the derivative rules. And if I have y squared, for example, what will be the derivative of y squared? Is it 2y? It is not 2y, it's 2y y prime. Because like u squared, right? We saw that by chain rule, we have to apply the chain rule. Chain rule says that, let's say if you have u squared derivative is 2u u prime, not just 2u. Instead of u here, which was assumed to be a function of x, here we have y, which is also a function of x. So the concept, we have to apply the concept of chain rule to differentiate the terms that contain y. That's the only thing that is important here for the implicit differentiation. You have an equation, it has left-hand side, it has right-hand side, just differentiate both sides. But the terms that contain y, for differentiating them, you have to multiply them by, it's the usual derivative times y prime, which is implied by the chain rule. And that's the only important thing. The rest is very straightforward once you know the different derivative rules. So let me tell you, let me write this way that find y prime, our goal is to do that. Differentiate given, so we said given and yeah, differentiate both sides of your equation using derivative rules and have in mind that the derivative of terms that contain y must be computed using the chain rule meaning that they must be multiplied by y prime. I.e., they, when I say they, I mean the usual derivative. The usual derivative must be multiplied by y prime. So let's look at an example. Consider this is y squared equals x. So part A, find y prime equals dy to dx. Okay, before moving on to the next example, have in mind that the derivative of terms contain y must be computed using the chain rule. And then remember, we wanted to find y prime. Then isolate for y prime. Isolate for y prime. And solve for y prime. So isolate for y prime means keep all the terms containing y prime to one side and keep the other terms to the other side, and then you can solve for y prime after you apply the chain rule for the terms containing y. So I will show you the steps in examples. So for example, consider y squared equals x, find y prime equals dy to dx. Part B, find the equation of a tangent line at the point, let's say 4 and 2. Part C, verify your answer by finding the explicit equation and using derivative and use derivative rules. Use the standard derivative rules. to verify your answer. Okay, so here, what is the equation that is given to us? Given the given equation, what is it? Y squared equals x. Now we said we have to differentiate both sides. So differentiate both sides. So then we need y squared derivative equals x derivative. Now y squared derivative, what is it? So by chain rule, we can say that y squared derivative is equal to 2y y prime. So that's the important thing here, that the chain rule says that, for example, when you have u squared derivative, is going to be 2u. Yes, 2u, but multiplied by u prime. Because f of u derivative is f prime of u times u prime. Chain rule says f of u derivative is f prime of u times u prime. So u squared derivative is 2u times u prime. In this case, instead of u, I have y, but still the same concept. What was u there in the statement of the chain rule? What was u? U was a function of x. Well, here y is a function of x. So instead of the letter u, I'm using the letter y, but still the same concept as the chain rule. So still I have to apply the chain rule, of course. So if y squared derivative is 2y multiplied by y prime. So 2y y prime equals derivative of x, which is 1. And then that gives y prime equals 1 over 2y. So then, let me write it step by step. So 2y y prime plus 1. Isolate for y prime, which is already done, right? Isolate means what? Means taking everything containing y prime into one side, and then the other terms are in the other side. Well, it's already in that form. All the terms containing y prime, there's only one term containing y prime, which is 2y y prime, and that's in the left-hand side, and then the other term, which is 1, in the right-hand side. So it's already isolated. I don't need to do anything. And next, solve for y prime. And then I'll get y prime equals 1 over 2y. Okay, so we conclude that y prime equals dy to dx equals 1 over 2y. And then part B says find the equation of tangent line at 4 and 2. So for part B, at the point 4 and 2, y prime at the point 4 and 2 is 1 over 2y at the point 4 and 2, right? It seems the screen is freezed. Right, let me stop share. Okay, y prime was 1 over 2y. We have to evaluate it at the point 4 and 2. How much is that going to be? Y value is 2, so 1 over 2 times 2, which is 1 over 4. It's 1 over 2y. So if I want to evaluate it at the point 4 and 2, I have to look at the y value because it's 1 over 2 times y, right? So the y value of this point is 2. So I have to, when I want to evaluate it at the point 4 and 2, then I have to use the y value, which is 2, replace it here, and I'll get 1 over 2 times 2, which is 4. What about the x value? Well, I didn't use it because in the expression, I don't have any x appeared, right? So if it was, for example, x over 2y, then if I want to evaluate x over 2y at the point 4 and 2, well, I have to replace x with 4 and y with 2 and evaluate at that point. But in the expression for my answer, for the answer for y prime, there is no x appeared, only y's appeared. So I only need to know the value of y, which is 2 at the point 4 and 2. So I use that, and then I get 1 over 2 times 2, which is 1 over 4. All right, now part C says that we have to verify by finding the explicit equation. What is the explicit equation? So y squared equals x. So y will be equal to, so explicit equation will be of the formula y equals plus minus root x. Right? So if y squared equals x, y is plus minus root x. And therefore, what is y prime? Y prime, we can use the derivative rules. So plus minus root x derivative. So that means plus minus x to power 1/2 derivative. Root x means x to power 1/2. And then it's going to be plus minus 1/2 x to power 1/2 minus 1, right? X to power m derivative is m x to power m minus 1. So x to power 1/2 derivative is 1/2 x to power 1/2 minus 1, which is plus minus 1/2 x to power minus 1/2. That's plus minus 1 over 2 root x. Now, at the point 4 and 2, x is positive and y is positive too. Y is basically positive. Okay, so now because y is positive, we can say that the y value is positive. So we can say y is equal to root x around this point. Right? Because when I say y cos, we said y cos plus minus root x, but minus root x is rejected here because if it's minus root x, then y value will be negative because root x is positive. So minus root x will be negative. But here y value is positive. So we can say y is root x. And therefore y prime will be, so our calculation. So y prime is plus minus 1 over 2 root x, but minus sign is if this minus sign here is for this minus sign here. So, but this minus sign was rejected. So this minus sign will be rejected too. And we had this plus sign here. So which corresponds to this plus sign here. So y prime will be 1 over 2 root x. And therefore y prime at the point 4 and 2 will be 1 over 2 root 4, right? This time we just need the x value because only x is appeared. And remember, we're working with explicit equations. So right-hand side, naturally, as expected, only x appears. And at 1 over 2 root x at the point 4 and 2, x value is 4. So 1 over 2 root 4, and that's 1 over 4. Same answer as before. As B. And we also needed to find the equation of tangent line. And what is the equation of the tangent line? We found the slope. We also need the equation. Equation of tangent line. Hence, the slope of tangent line at the point 4 and 2 is m equals 1 over 4. And therefore, the equation of the tangent line the equation of tangent line at this point will be, what will it be? Y minus the y value, which is y minus y naught equals m times x minus x naught, and x naught y naught here will be 4 and 2, and m is 1/4, so y minus 2 equals 1/4 times x minus 4. So this is the equation of tangent line at the point 4 and 2. Okay, let's look at the next example. Consider the equation, the implicit equation. Implicit equation, let's say xy equals 1. So part A, again, find y prime equals dy to dx. And part B, again, verify part A, verify your answer. Your answer in part A by writing y in an explicit form. I say in the explicit form because it's just one form, y equals a function of x. So how can I find y prime or dy to the x? Like the recipe tells us that we have an implicit equation to find y prime or dy to x. First, we have to differentiate both sides. Okay, so first, differentiate both sides. Then we get xy derivative equals 1 derivative. That gives 1 times. So this one, for the derivative of the left-hand side, I have to use the product rule. Remember the differentiations, and when I say take derivative, of course you have to do it with the derivative rules. Now, which derivative rule should I use here? It's x times y, it's product of two functions, x and y. So I need to use product rule to find the derivative of product of two functions. So then I can apply product rule. And then I'll get x derivative times y plus x times y derivative equals derivative of 1, which is 0. Derivative of constants are 0. And therefore, and now x derivative. So when I say derivative, I mean d to dx. So x derivative, which is same as dx to dx. Derivative of x respect to itself is 1. So then I'll get 1 times y plus x times y prime equals 0. And then I have to next isolate for y prime. Which means keep all the terms containing y prime into one side and all other terms the other side. Then I'll get xy prime equals minus y. And then that gives me y prime equals minus y over x. Let me write after isolated, we say next solve for y prime. And then there we'll get y prime equals minus y over x. That's it. When you isolate for y prime, you will have all terms containing y prime to one side and other terms to the other side. Then you can factorize if necessary, but this time, similar to previous example, we had only one term containing y prime, so we don't have to factorize. In the next examples, I will show you the cases where we also have to factorize for y prime and then solve for y prime. But here it's just one term containing y prime. So we have just xy prime equals minus y. There's no need for factorization. And then just solve for y prime, which means just divide both sides by x. And then we get y prime equals minus y over x. So part B, verifying our answer. So we want to verify by writing in the explicit form. What is the explicit form of xy equals 1? We have xy equals 1. Explicit form is y equals a function of x. Then explicit form will be y equals 1 over x for x not equal to 0, of course. Or I can say this with that note that, xy equals 1 implies that x not equal to 0. So we can divide by x. Right? Because in mathematics, you have to always be careful. If you want to divide by a number, you have to make sure that that number is non-zero. If you are not sure whether it's 0 or non-zero, then you can consider cases or write it as a piecewise function. But here I don't need to write it as cases or piecewise function because I can be sure that x is not 0. Why? How can I be sure that x is not 0? Because if x is 0, 0 times y will be always 0, not 1. So there is no y value corresponding to x equals 0. So that means I can be sure that x is not 0. In other words, this equation, this equality implies that x is not 0, because if x times y is something non-zero, that means both x and y must be non-zero. Here, I just want to use the fact that x is non-zero because I want to divide by x. So I use the fact that x is non-zero, then divide by x. And then we get y equals 1 over x. So this is an explicit equation. So this is explicit equation corresponding to the equation xy equals 1. And then I just need to use derivative rules to find y prime. So we can say that y prime, which is dy to dx, is what? Is just simply derivative of 1 over x, and which means derivative of x to power minus 1. Again, x to power m derivative was m x to power m minus 1. So minus 1 x to power minus 2, which is a minus 1 over x squared. So is this same as the answer we got in part A? A, we got y prime equals minus y over x. Part B, we got y prime equals minus 1 over x squared. Are they the same? So note, answers in part A and B are the same. Are the same because in part A, we got minus y over x. But what is y? Y is 1 over x. Y is 1 over x. And this means this is minus 1 over x, and that's minus 1 over x squared. Right? Minus y over x was the answer we got in part A, and y, we know it's 1 over x. We wrote it here. So when we substitute y with 1 over x, we get minus 1 over x, which is minus 1 over x squared. The answer we got in part B. Okay.